Hello, everyone, and welcome to Alt-Tab. Alt-Tab is CSC's Tech Talk event where students give talks to other students. This term, we have an amazing lineup of speakers that I'm very excited to introduce you to. So first up, we have Ryan, who will be talking about probabilistic programming languages and how they're used for Bayesian inference. Next, we have Dmytro giving a talk about deniable disk encryption. After that, we have Eric, who will be talking about tracing in microservices and also give a look into a popular open source tracing system. And last but not least, we have Addy, who will be giving an intro to metaprogramming in Typescript. At the end of each talk, we'll have a 5-minute Q&A with the speaker. If you have any questions during the talk, ask them in the Twitch chat or drop them in the anonymous Slido, and we'll do our best to have the speaker answer your question. And we'll be dropping the link in the Slido right here. Okay. All right, let's get started. First, let's welcome Ryan. Ryan is a CS22 student who will tell us about probabilistic programming languages. Welcome, Ryan.
Hi, can you all hear me? Cool. I don't know where the present button is, so this is what we're going to do. Hi, everyone. I'm Ryan, and we're going to be talking about probabilistic programming languages. They're a hidden gem in computer science, and I don't think you get exposed to them otherwise. So I hope by the end of this introduction, I can convert y'all to web people. And that's a joke that you'll all get by the end of this talk. So let's start off by introducing a problem. How can we make machines that think like people do? Okay, well, how do people think? So we kind of have some understanding of how the world works, we as people, and we have this kind of small model of the world in our heads. And it tries to explain everything we see in the large world around us. And as we observe events in the real world, in the big world, we learn and we change our model in our heads. So we update our small world. Okay, so that's one way that humans think, right? What's an example of this? Can we go through an example of this? Okay, well, how about tug of war? So an example of what a small world is, or a piece of a small world could be, is, in the real world, there are people, people exist, and they have some degree of strength. And if two people play a game of tug of war, for people who don't know, tug of war is when you have a rope and two teams kind of pull on the rope. So in general, when two people play tug of war, the stronger one probably wins, right? So this is kind of the small world model that you have in your head. So if you see me playing tug of war with Jason, okay, and if Jason wins, every one of us that sees this would believe Jason's probably stronger than me, right? It's not surprising, because in our small worlds, the stronger person wins, and Jason would then be stronger than me in our model of how the world works in our heads. And because we kind of understand how people work, because we understand how tug of war works, if we had to guess whether Jason would win against a stranger, who would you bet on? Would you bet on the stranger, or would you bet on Jason, knowing that Jason beat me? You don't know anything else about me or Jason, but you probably bet on Jason, right? You wouldn't be very certain, but with what you know about how people work and how tug of war works, that's what your small world would predict, okay? So simply put, we as humans have kind of structured information about how the world works. And as we observe new information, we can learn and change the structure of the world. But we can also use the structure, we can use our small worlds in order to understand new problems and solve new predicaments. So we can solve stuff like whether Jason would beat a stranger at tug of war, even though that's kind of an unrelated problem, right? We've never observed this, but we can extend our models. So I guess this introduces a new problem to you guys. How would you build a machine that can think like this? How would you build a machine that can understand tug of war? Right? So if we're looking to build machines that think the way people do, this is kind of a very simple problem, right? And I think the most intuitive solution, using first-year computer science, you write a deterministic program in C++. What do? You probably just sort people based on who won against who, right? do some sort of topological sort. So your first heuristic, and it kind of works, right? You'd be able to understand if Jason beat me, he's probably stronger than me. So you return, yeah, Jason's stronger. But what does this program really do, right? It doesn't really understand uncertainty, and it doesn't really understand what people are, right? It doesn't extend to new situations. So what if you were really hip, you're well versed in the literature, you understand modern ML, you could train a neural network. So neural networks are all the rage, just a lot of research on it. And what you can do is you can train this neural network to predict who would win at tug of war, right? So how would you do this? Well, you'd have to give it two inputs for the two teams. And then after a million training examples, your neural network probably, not definitely, it'll probably be able to memorize who wins, right? So you'll give it two arbitrary people and it'll kind of spit out who wins. But really all it's doing is it's memorizing the players. This neural network will fit your data and it'll memorize the data. So it'll be able to kind of reproduce the tests and questions it's seen so far. But it doesn't really understand anything about people, right? So in modern ML, when you train neural networks and you try to use neural networks to solve and understand a game of tug of war, you don't really understand anything about how the world works, really. So let's approach this a third way. I'm sure all of you intuitively as people would know how to solve this problem. You see all this stuff about tug of war, and I asked you who's stronger, you'd be able to do it by hand, right? And if you've taken a statistics course, or you plan to take a statistics course afterwards, you'll be able to solve this by hand. Unfortunately, some of these problems are actually kind of impossible to solve analytically. So no matter how smart you are at math, like you literally cannot do it. So not only are some of these problems kind of intractable, we call it intractable if computationally it's infeasible to calculate the solution to some problem. What we really want, we don't really want you to do it by hand, right? We know you know the answer. We want to be able to create a machine that thinks and learns from examples the way we do. So how do we solve this problem? How do we write a program that understands tug of war? So to solve this, we introduce an idea of probabilistic programming languages. Okay, so that's the topic of this talk. What are probabilistic programming languages, or PPLs? PPLs, or people, are a tool to describe your small world in code. Okay, so let's just go to an example of this. This is WebPeople, a very simple probabilistic programming language. And what these languages allow you to do is pretty simple. So you have your small world, your notion of how the real world works, right? Your simple model. And probabilistic programming languages allow you to represent this model to describe the structure of how things work in code, right? It's a very good way to express things, you might say, to express a system. And using PPLs, your machine can kind of learn humanly. You can learn the way humans learn and adjust to new information, as well as apply your kind of structured understanding of the world to new problems. So the cool thing about this is it's well motivated, right? And not a lot of people know about it, but the tooling exists to make this kind of problem very easy. And I think that should excite a lot of you. So this specific example for tug of war is taken from the MIT CBMM tutorial, but unfortunately they kind of run out of time, so they don't really go through the tutorial. So we can kind of think about this as an extension to their talk. So this is really a very simple tutorial of tug of war, and hopefully you can all see my screen. If you guys can't see my screen, well, I made very beautiful slides, so that would be kind of a waste. But what we're doing in this language are we have just very few lines of code that explain how tug of war works. So we don't have to really look at this, the bottom stuff, right now. So we can kind of just look at the top part. Okay, so let's comment out the bottom part. We just look at the top part. What are we doing? We have this model of tug of war, and we're saying here's strength. It's a function. If you're familiar with functional programming, you should feel right at home. So it's strength is a function that takes in a person. So, given a person, they have some sort of strength, and we're just saying their strength, their prior for their strength comes from a Gaussian distribution. So we're saying an arbitrary person, a stranger, has a strength of 50. We don't really know how strong they are, but we're saying like there's some kind of uncertainty around 50. Okay. And we kind of introduce this extra complexity where we're saying, when people play tug of war, it's not really deterministic, right? If Jason and I play tug of war and Jason is stronger than I am, he probably wins, but he doesn't always win, right? He might not try very hard, or the grass could be slippery. So we're going to say, with some probability, 30%, Jason's kind of lazy. So he doesn't try very hard if he's really lazy. Okay. So then we say, people pull on the rope, right? That's how you play tug of war. So how hard do they pull on the rope? Well, if they're lazy, they pull at half strength. And if they're not lazy, they pull at their full strength. That's all we're saying. So how hard does a team pull in tug of war? Because when you play tug of war, there are a lot of people. You can have multiple people on both sides. So we're just saying, how hard does the team pull? It's just the sum of the individuals. It's the sum of how hard each individual person pulls, and that's all we're doing. It's just sum over that. And then the winner between two teams is just the team that pulls hardest. Okay. So you can kind of see the code here is not very complicated. The system is fairly structured, and to do this with a neural network or with like a deterministic program would be very, 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 very difficult, near impossible. But with probabilistic programming languages, we can kind of describe how the world works very intuitively and very naturally, right? So this isn't a lot of work, it's not a lot of complexity, but we're able to describe a somewhat complex program or a somewhat complex state of the world. So let's just do a sanity test. You don't know anything about me, and the program, I've commented out, the observations, and I ask it, how strong is Ryan? Okay, what do you think it's going to say? Well, probably around 50, right? It'll give a Gaussian distribution with variance 10, around 50. Might be standard deviation 10, but anyways, it's a Gaussian distribution around 50. Okay, why does it say this? Well, it's never seen anything about me, so it's just giving its belief about how strong a person is, right? It's giving its belief represented as a distribution for a stranger, right? Because it has no data about me. But let's say that we do have an observation, right? So we want to be able to build machines that learn from evidence and from events fast and normally. So let's say we observe that I beat Jason at tug of war, right? How strong do you think I would be? Well, as a human, you'd be like, okay, well, I don't know anything about Jason, right? But if Ryan beat Jason and Jason's kind of like a stranger, Ryan's probably stronger than average, maybe. That'd be your belief. You'd be pretty uncertain about it, right? Because I just beat one person. Maybe Jason's just lazy. Maybe Jason's like really, really weak. We don't know anything about Jason, so you wouldn't really know. But the nice thing about probabilistic programming languages is that now that you've described the state of the world, you've described the small world, just given observations, we can use Bayesian inference in order to give necessarily the optimal belief on your posterior. And if those words don't mean anything, don't worry about it. All I'm saying is, you can kind of just find out. You've described how the world works, and well, Ryan is probably stronger than 50. If 50 is average, Ryan's probably stronger than average. Okay, that makes sense. So what if we observed more than that? What if we have observed that I beat Jason and I've also beat Gordon? Gordon just being some other guy, right? So how strong do you think I am? I'm probably even stronger now, right? You're probably more confident that I'm stronger than the average person, right? And the reason why these aren't perfectly Gaussian is because we're doing this kind of numerical sampling and computing, right? So we're not solving things analytically, which is why this extends so well. And that's what the noise you see in the distribution comes from. But now that we've observed that Ryan has beat two people, Jason and Gordon, Ryan's probably pretty strong. So then you might ask, okay, would Ryan beat a stranger? Probably, right? Because if Ryan's pretty strong, and unless both Jason and Gordon are really weak, we can just kind of extend our model and say, okay, beat is a function that what? Takes in two teams. Let's call a stranger Max, okay? So Max is just some other guy. Would Ryan beat Max? How confident are we? Well, probably fairly confident, right? Like, I'm pretty strong. We don't know anything about Max. So I'd say, yeah, he'd probably beat Max. And our model for this, right, our probabilistic programming language tells us, yeah, that's probably true. what if, and we've observed that I've beat Jason, that I've also beat Gordon individually. How confident are we that I would beat both Jason and Gordon working together on a team, right? So how do we find out? The code for this is very simple because we've already defined our small world. Every extension on top of that is very simple code-wise in a probabilistic programming language. So in this case, we're just saying, okay, let's find out whether Ryan as one team would beat another team composed of Jason and Gordon. And intuitively, we should think, no, right? He can't. Why? I mean, if the average person has a strength of 50, right? I might be stronger than Jason and Gordon individually. They might be like 45 or 40, but both of them together, that's probably unlikely, right? And if we ask the PPL, would I beat both of them working together? Probably not. It's not definitely no. There's about what 70%, 7% chance that I actually do beat both of them, given what we know. But we can get very informative estimates about the state of the world using this kind of method. And it's a very powerful tool that not really a lot of people know about. So this was really just a very simple example, an introduction to probabilistic programming languages, how they work, and the motivation behind them. Thank you for listening. Are there any questions?
All right, thanks, Ryan. We actually do have one question right now, and it is, why isn't PPL used over ML if it's more extendable than neural nets?
Okay, so, right, let's see if you can solve this without asking me. Just for the information, all right, we have these things called neural networks, and we have these things called PPLs. What are PPLs really good at? Okay, so in the tug of war example, and you're kind of biased because I just gave this amazing presentation, right? PPLs are fantastic. Well, what PPLs do is you have this structure about the world, and it does this thing called Bayesian inference to understand and update its model in the world based on structure. What if you have a different kind of problem? What if the problem we're trying to solve is in computer vision, right? So you're given a image of an animal, and you want to say, what kind of animal is it? How would you write a PPL for that? The issue there is, you're not working in a semantic space anymore. All the stuff we've defined here, we've defined kind of a data story. We've defined a graphical model. We've defined kind of a story for how things work, but we're all working in this kind of high level space. We're working in the way people think, but sometimes the data is not in how people think, right? An image of an animal is not going to be in terms of text or in terms of high level objects. It's going to be in pixels. And you have this very high dimensional space that you need to work on. And suddenly, you don't have structure, right? You don't have kind of intuitive structure the way you do in these real world systems in like a game of tug of war. When you try to understand the structure and you try to understand the world in this kind of pixel space, in this very high dimensional space, really all you want to do is memorize, right? You want to understand the structure that exists because as humans, we don't think in high dimensional spaces like that. So to answer your question, why don't we use PPLs more extensively? Well, part of the reason is they're just not very well known. So there are a lot of like cases where you might actually do the math analytically for Bayesian inference. And if you work at like a trading firm, if you work in research, you probably do that. But especially, there are definitely cases with high dimensional data or cases where you want to model something that's not necessarily in the same space, in the same logical space that people think about. And there, you don't have the option to use PPLs. So I hope that answers your question. Do you have
Awesome.
another one?
Yeah, there's actually another one. How are you introduced to PPLs? Are there any courses or resources to learn more?
Okay, so I'm going to assume you are a Waterloo student. I'm very glad you're excited about this topic. It's kind of, the idea of Bayesian inference has been along forever, and PPLs are just kind of syntactic sugar or a reduction on Bayesian inference. If you go to Waterloo, you'll take stat, and then eventually you'll take like stat 370, and stat 370 is a computational stat course on different types of high dimensional sampling. So how PPLs work under the hood is kind of introduced in that course. So if you're familiar with Monte Carlo simulation or MCMC or like different kinds of sampling methods. It's a very nice course in order to understand that, but they don't go into PPLs. There is a grad student course, and if you didn't know, you can in fact take grad courses as an undergraduate student. Just make sure you know what you're doing, right? But there is sometimes a grad course that's offered at the University of Waterloo on PPLs. If you're in a rush and you really want to know right after this, there is an amazing paper summary. So there's a paper survey, kind of long, but it goes into the details of this on arXiv. And you can always go to kind of the prefix tutorial on MIT CBMM. So if you just kind of Google probabilistic programming languages online, you'll find lots of great resources.
Awesome. Thanks so much, Ryan. I think that's all the questions for now. So thank you again, Ryan. And we're going to move on to our next speaker. So our next speaker is Dmytro, who will be giving a talk about deniable disk encryption. Yeah.
Okay, you should be able to see me now. I hope nothing's broken. Okay, so deniable disk encryption. I'm sorry, this is an overview talk, so if you already know this, it'll be boring. But if you don't, it might be exciting. Disk encryption. It's a good idea. You should do it. I do it. The general stance in security, though, is that you should know who are you protecting against, and you imagine the strongest enemy you wish to protect against, and you see if you are achieving your goal. So in disk encryption, who are you protecting against? Well, laptop thieves, for example. I carry my laptop with me often. Maybe I leave it unattended for a moment, it gets stolen. Don't want that random person see my personal data. Well, there are actually ways to defeat disk encryption, though, right? And one of such ways is if the laptop is powered on, you can connect a special device to privileged bus, such as PCI. You can use DMA to extract data from memory, RAM, I mean, including encryption keys, which are there while the device is powered on, so you lose. That doesn't work with devices with I/O MMUs, which is becoming increasingly common in laptops today. So what can you do then? You can do this, for example, called boot attack, pretty well known. You can read, there's a paper on that. You freeze the memory with liquid oxygen, for example. While the device is powered on, then you power it off, you extract the memory, put it in another device, you read it, you can find the keys there. Either way, your encryption is defeated. Now, I'm not worried personally about either of these things, and the reason I'm not worried is that a random laptop thief is not going to have the equipment to do this, and they're not going to bother because my data, the expected value of my data is not nearly high enough to go through this. Now, some other parties are actually well equipped, such as the police. If I were committing crimes, I would be very concerned about this being deployed against me. And so if you're an interesting person, such as these two gentlemen and many more who also deserve to be here, then you might actually ponder how to handle police and other state-level adversaries, the FBI, what have you. And the answer is obviously that it's hard. Most security solutions don't live up to that, the promise of security against such adversaries. But let's consider it anyway, because that's what we do in security. We play around with stuff. So from the point of view of law, strictly speaking, actually we're in luck, we in Canada at least, and in the US, because the legal framework that we have provides strong defense against self-incrimination. Fifth Amendment in the US, Section 11C in Canada, say that you cannot be compelled to testify against yourself. And if you are, then that's not usable in a criminal trial. Now, passwords turn out to be a form of testimony. So if you have an encrypted disk and the police ask you to provide your password for the disk, you don't have to do it. That's testimony. That's not true in many places in the world and anywhere else in the Commonwealth, as far as I know. For example, in the UK and in Australia, it's particularly untrue. In the UK, you can go to jail for 2 to 5 years for failing to disclose your password. The police don't need a court order for that. In Australia, I believe it's 6 months, something like that. But you will be criminally charged for failing to provide a password. again, nothing specific needs to be known about what's in your disk. You just have to surrender it in case there's a search. So that's obviously a problem. Now, you see that the top two countries actually are against a yellow background, so this is not bulletproof by any means. If you're crossing a border, you'll be in trouble because the border agents have certain liberties. They can seize your devices. You'll have a lot of trouble even if you refuse to provide passwords. And if you are a foreign national like myself, if you're here on a visa, you can be denied entry to the country for failing to provide decrypt your files for border agents. So that's a privilege to enter Canada, and you're not entitled to it. So in many countries, and even here for these reasons, you might have to decrypt your data. And even strictly in criminal proceedings, there's a lot of very involved nuance in the case law. For example, you can actually be compelled to provide passwords in some cases. There's a great Harvard review that goes into details. It's about 70 pages, but every page is worth a read. If you're planning to commit crimes in the US, you should definitely read that review. And for example, in this case, in the Gelfgott case, the defendant actually admitted that they were able to decrypt files, but they refused to do so. And it turns out that testimony actually is protected. Evidence in general is not protected. In general, you have to surrender evidence, right? That doesn't protect you against self-incrimination. But the passwords are protected because they are not, though testimony are evidence, they're a special category of evidence. But it ceases to be such if you are not communicating new information. So the reason passwords cannot be compelled in general, one of the reasons is that you're implicitly communicating the fact that you can't decrypt the data. And it turns out that that's something that is protected by the Fifth Amendment. But if you volunteer the fact that you can, in that particular case, it turns out you lose your Fifth Amendment protection in the US. The authorities compelled Gelfgott to decrypt his data, and the court ruled that that was correct. He didn't have the right to refuse. And there's also the foregone conclusion doctrine. Basically means if the state already knows which files you have on your disk, then you have to provide them. You're not communicating anything new by decrypting them. So it's a pretty thin defense that you have there. And in many countries, the defense kind of is irrelevant. They don't have a strong judicial system, and you can be physically coerced. Some countries ground planes to detain journalists. So there you'll be subjected to the most compelling form of attack on encryption, actually, which is physical force. It's called rubber hose cryptanalysis. There's an XKDC about that, XKCD. And I find the name of it strange. So the idea is you beat a person with a rubber hose until they give up their password. Rubber hose, because that doesn't leave marks. It's a little strange. The Russian term is thermorectal cryptanalysis, which I find much more evocative. But the idea is clear. Now, that's one extreme. On the other extreme, there may be a friendly request. Maybe you want to provide a decoy for your spouse, for example. You don't have to. You don't have any obligation to show them what's on your disk, but maybe you want to. And you may want to decrypt something innocuous instead of whatever you have there. So for all of these reasons, you might like to achieve these goals listed below. And all of that is jointly achieved by what's known as deniable encryption. It's a form of encryption where you can avoid giving up your actual data under duress, essentially. And we will see how it's done. There are a few ways to do that, as usual, more and less involved. But first, for something kind of different, it is actually a form of deniable encryption, but none of these. Let's talk about steganography, because it is an instance of that. Steganography is the art of hiding in plain sight, such as, for example, writing with invisible ink is a form of steganography. Another form, which will be well known to you if you are a CDF player, it's a toy example, is where you hide data in the least significant bits of an image. That actually is a reasonable way to go about things, kind of reasonable. So here's an image. These images look the same, but actually the right one is a transform of the left one. And the least significant bits, if you look at them, this is a really good substrate to hide data in. So the right-hand side here is the ciphertext. It's an encrypted text file. And the left-hand side is the original bits of this image. And although they look quite similar, you will see that this is uniform noise and this is not uniform noise. There are some impurities here. It can get much worse. That was a real best case image. Look at this image. Well, turns out that this is mostly uniform color, so this really is not uniform noise at all. And you'll see that this is really implausible as least significant bits of that image. So you can actually detect that something has been embedded there. There are ways to protect against that, but it's an arms race. You're sort of trying to evade statistical analysis, and forensics experts are trying to improve their analysis. So this is not what is done in practice, but it's interesting to know. Okay, that's that, and we'll come back to this. But first, let's talk about, in fact, what's important about this, again, that encrypted data looks like uniformly random bytes. That's an important property of practically used encryption. And so what this means is, really, if you have encrypted disk, what betrays the fact that it is encrypted is the headers on the disk. If you use LUKS, for example, which is a standard Linux way of encrypting disks, then there will be a header on a partition that's encrypted, which shows that it's a LUKS partition. Now, with LUKS, you can, for example, detach the header. You can use this setup where you put it on a USB drive and you carry the USB separately, and you don't need to carry it with you through an airport, for example. And without the headers, then the data just looks like random noise, which is what you want. It's impossible to prove that it's encrypted data and not random noise. And some other encryption systems don't use headers at all. And you can use LUKS without headers. So not only can you detach them, but you can avoid the use of headers at all. This is one example. And in fact, it has been held up in the US that random noise is not sufficient grounds to think that there are encrypted files. There is not a foregone conclusion that there is encrypted data where you see random noise, even if it's implausible. So this is not plausibly deniable. If you have a disk, if you're traveling with a laptop and the contents of the disk are random noise, it's implausible that there's no encrypted data there, right? Why would you be traveling with an empty disk securely erased? That's very implausible. You may be doing that, but it strains credibility. Regardless, it stands up in court of law in that way. And in general, that's a fairly easy thing to do. Now, if you want to take it to the next level, which is a good idea, this bare bones, and you can fairly easily do the next level, which is have a hidden volume. So the idea is that you have multiple encrypted partitions, 2 of them. First is a decoy, and there you have files which are not sensitive, or which they should appear sensitive, so that you have reason to hide them, but they're not what you're actually trying to hide. What you're actually trying to hide is in here. And how it's actually set up is that there appear to be only these 2 partitions. The hidden one is not visible. There are 2 encrypted partitions, and you will have to explain why you have 2 of them, right? But that's fairly easy. There are multitude of explanations. Say, oh, I have my documents here and I want to separate them. It's not that implausible. There are many more. TrueCrypt website talks about this. And the key part is that this hidden partition is hidden in the free space of the second partition, which means, so there are no headers. TrueCrypt doesn't do plain text headers. And you can fairly easily then hide it just in the free space after all of your occupied space. You just have to freeze the contents of this partition in place. You can store photos there. Your photo collection has been added to in a long time. That's a setup that's commonly used. It's fairly good in that, really, it's quite plausible that you don't have any hidden volume. There are some attacks which are described in this paper, although they're kind of questionable, I would say. You should read it and make up your own mind about that. But one weakness of this, which is definitely present, is that, well, if this is free space here, then how come if you ever are apprehended with a device which, for example, records the staleness of sectors when they were most recently written to, which SSDs do, for example, they have write counts on their blocks, or you are apprehended twice, and the image your disk can compare the before with the after, then it's implausible that your free space was written to overwritten, right? And the data didn't seem to change. So that will be a problem. You can run differential analysis on this kind of setup. And this was noticed, and smart people, including Assange co-authored this actually, RubberHoseFS, which is a steganography-based solution, which really tries hard to do this as smartly as possible. You can have any number of aspects in a disk, and an aspect is really a bunch of chunks like that are strewn around the disk. And the key idea is that there's no clear delineation between them. So your patterns of writes will appear to be randomly, uniformly distributed. And if you unlock the first n aspects or any subset of aspects, then you don't know if there are any left. For example, these three are here, and there's also a yellow aspect, which I didn't show here. But if you open only the top three, then it's not clear whether what remains is free space or there is other data here, or there's other data hidden there. And you can never prove that you have unlocked all of them. That's really crucial. Assange argued that that protects you, that if you're in an organization, that protects you against defectors in your organization, because they can never, under torture, prove that they have revealed all of the keys. It's impossible. So they will be less inclined to reveal what's valuable because they know that torture won't stop. They won't be able to prove that they have revealed everything. So that's important game theoretically also. Then all of these are designed for hard drives, meaning non-flash media. Flash media introduces complications, which I don't have time to detail very much, but basically the idea is that there's a mapping between pages and blocks of the underlying flash. It's called the flash translation layer on SSDs, and that thwarts your statistical sort of protections, because you can see that you can kind of see the sequence of writes to pages, and you can infer that something is not free space, but is actually was written to, is a hidden partition. And there's a file system that circumvents that by being smart, by using by scheduling blocks by itself and using blocks from the head for the public partition and blocks from the tail for the hidden partition. That's the broad strokes. Now, there's a question, obviously, of whether this is actually practically, does it provide plausible deniability? If someone's looking for specific files and you've decrypted your k first n aspects, let's say, in RubberHose, and the files are not there, and they're sure you have them, then it's kind of useless, right? They know that you haven't revealed all of your keys. But there is a broad, I think, there's a large number of circumstances where it can be useful, which are not that, when the other party is not certain what it is exactly that you have, then it can be useful. And it's interesting to think about. And that is all from me, and I open to questions.
Awesome. Thank you so much, Dmytro. Yeah, I hope you won't be involved in any crimes anytime soon.
No, it's not my intent.
Yeah, I know. I'm just joking. So I do have a question. You talked a lot about deniable disk encryption. So that's like deniable encryption for disks. But what are some examples that you know of where deniable encryption outside of disks is useful? Like, say, in passing messages.
Yeah, that's sort of, I didn't cover it because it's almost entirely different ideas that are used there. Well, not necessarily entirely different, but it is a thing. You can do that. One of the interesting ways in which you do that is, well, it'll take a while to detail, but you can actually, Wikipedia talks about it, for example. So there's actually a decent article on that. But you can do that. You can deniably pass messages. And the idea is that, for example, you have a message which is innocuous, and you pass it along, and you have a message which you actually want to pass. And one way to do that is by sending it in tiny packets, and have some packets which are, let's say, 1-bit packets, and some packets are legitimate and others are not. And you know that via an authentication mechanism. But later, you can, and you have 2 authentication keys, and one of them is the real one and the other is not. But then when someone presses you, you say, oh, I received this innocuous message, and you show that, this stream of packets is the right one, and the other ones you say are, well, so the difficulty is, what about the other packets, right? And I think the setup there says, well, these are just garbage, they are malformed, for example, because they don't pass validation. Now, someone who is familiar with this will say, no, there's definitely a second message there. And I don't actually remember how that's handled, because that's not the topic of this. I actually saw that accidentally and thought, oh, this is pretty neat. But I'm sure you can expand on that idea somehow. But it's a different idea, right? Because there you have an active passage of messages over a channel, which is not the same at all as encryption at rest.
Right. Yeah. That makes sense. Okay. Thanks.
Yep.
Another question I had was, so these like encryption concepts, is there like some kind of course at Waterloo that viewers could take in order to learn more about it?
I don't think on this specifically, I'm not aware of one. There are graduate courses regularly in the CS department which talk about some advanced encryption stuff. Like there's a course in mobile security, whatever that includes. I presume at least that talks about full disk encryption on mobile devices. I would think so. But I assume CS 458 touches on it in some capacity, but I have not taken that course, so I'm not sure.
How about something like steganography?
Yes, so that's what I mean, because there's a cryptography course, but that doesn't talk about these aspects of practically using cryptography at this level. And I would think that it's talked about in 458, but I haven't taken it, so I wouldn't know really.
Okay.
I think graduate level courses, at least some of the offerings probably touch on that, but it's kind of useless information because, well, in your 4 years, maybe such a course will be offered once or twice, and maybe not for the topic that you are looking for. So I would say that the more productive avenue would be to search for stuff on the internet. There's plenty.
Right. Okay. Yeah. That definitely makes sense. But I think that's all the questions we have for now.
Okay.
Thank you so much, Dmytro. We'll be moving on to Eric. We have Eric now, who is a CS25 student, and he'll be speaking about tracing in microservices. Welcome, Eric.
Okay, great. Hi, guys. So sorry about that. I'm a bit nervous. It's my first talk, so I hope this goes well. As a little bit of context before I talk into to go deeply into tracing, it's kind of important to talk about why I'm talking about tracing. So right now, I'm currently on my first co-op, and I'm actually working at a small startup as a backend developer. And something that this startup does, that's the trend for a lot of companies working web development now, is the microservice architecture. So if you guys aren't familiar with web development, basically, whenever we make a request on any website, for example, like Twitter, there needs to be some sort of server that processes it. And traditionally, this has always been done using monolithic applications, as in this one giant process that handles everything. For example, for Twitter, there might be different services such as the tweeting service, the retweeting one, maybe authentication, authorization. All of these are bundled up into a single process that handles all the requests. The problem with this monolithic kind of architecture is that it becomes kind of hard to scale, because every time that you want to kind of, let's say there's a lot of people on Twitter that tweets a lot, and you want to scale that up, you want to have more servers that handles all that requests, you need to scale up the entire application. You would need another authentication, authorization, and so on for each time you want another retweeting service. So the problem with this is that those extra services can take a lot of kind of resources and memory in the background that doesn't really kind of it's not really great for scaling up, especially at the size of Twitter. For this reason, there's been like kind of a big movement towards something known as microservice architecture. The basic idea is that instead of having these giant kind of processes that handles everything, you have it split up into the smaller processes that need to handle whatever they need to handle. So you'd have the authentication on its own, the authorization on its own, and they can like talk to each other through regular HTTP. And this way you can kind of redistribute the services across your servers and kind of scale up based on the service itself. So instead of kind of scaling up the entire process up, you can just scale up the tweeting service if you just want to handle more tweets. And so this sounds great, right? Like, why doesn't everyone just start using microservice from the start? Well, for one, it's like back then they didn't really need to handle all that scale. And also there's another issue that comes with microservices, which is that each outage can start becoming like a murder mystery, if that makes sense. Because there's a bunch of smaller different services that need to talk with each other, it kind of becomes really hard to know how they communicate with each other. I know for me, when I first did my co-op, I was really confused about how this entire system worked and like how, especially since we were using like a bunch of other stuff such as Envoy and a bunch of other services that might kind of confuse exactly what happens when I tweet or what happens when I do a single request. For this reason, we kind of need a bit more, data or a bit more kind of view into how this exactly works. We need some more observability. And so this is a kind of a term that's coined by people in the DevOps community, which is the idea that if we want to actually kind of efficiently debug, efficiently know how exactly our code is running in production, we need to be able to kind of view more into it. And so there are these kind of three pillars that they kind of use as a term. One of which is metrics. I'm just going to kind of briefly describe this so you guys can have an idea. One of which is metrics, which is the idea that our application over time uses different resources, and this kind of just outlines all that different resources taken up in a graph. Another one is logs, which is just basically a bunch of print statements that's all together, which is a great way and to kind of debug applications, and it's how we kind of all started out debugging, and it's actually used quite often. But finally, the thing I want to touch on, because it's what I've been doing in my co-op for a long time, is tracing. So the idea with tracing is that we don't just want to know kind of what happened, or like what exactly, or we want to know what happens whenever we do a single request. For example, when we tweet, we want to know, okay, what microservices is that one request calling? Like, when does it do SQL statements? How is this all correlated, right? And so it also kind of encodes not just what service leads to what other service, but also the latency of it. Like, how long does this request actually take? Because that can help with, let's say, debugging if there's any bottlenecks in your code, or if there's anything that's really causing like a huge slowdown in like your production code. And so what I'm going to kind of, there's a lot of different open tracing, there's a lot of different tracing solutions out there. And today I want to kind of just bring you guys along another tracing solution that's an open source one that my company is actually using right now, known as Jaeger tracing. So I'm just going to kind of show you guys a bit of history lesson actually before we go into the live demo. Jaeger tracing was first made by, it's actually written in Go, which is why you see the gopher as the logo. And it was first made by Uber, I think back in probably in the mid 2010s or so. And it's an open source tracing solution. You guys can check out their GitHub at jaegertracing/Jaeger. And it's free to use for you guys and actually free to use in production as well. So they also made kind of a demo application that I'll kind of take you guys along to kind of try to understand how exactly do we create this tracing service and why exactly is it useful. So this kind of, this demo application they just have different stores that you can kind of request cars to go to, right? Like a pretty standard system. And so, if you're designing an application like this, you're like, great, now I kind of, you design a system and you kind of want to debug this in actual production code. How exactly do you go about that? How, as well as what happens if there's someone new that wants to, help you build this code? So why don't we kind of look at the actual deeper dive into the code? So you guys don't kind of have to understand Go. I'm just kind of showing you guys a general, as long as you kind of understand general C syntax, you guys should be fine. So if we look at the different, this command folder here, this is just describing all the microservices that are being used, right? We can see there's a customer service that's being used, something called the driver service, something called the front end, which we can probably assume handles all of these kind of requests that we see on the front end, right? And then we can like continue and seeing that there's a bunch of different microservices. And when you first look at this in general, it's probably really confusing about how exactly do these different services talk to each other, especially as you scale kind of horizontally, as you add more services. If there's like 10 or 20 of them, it gets really confusing once you kind of onboard onto a new team. How exactly does this actually work, right? Like we can try to guess that, oh, we go to front end and we see this actually like kind of handles the HTTP request, but it's still really confusing about how these microservices are interacting with each other. For this reason, tracing is actually quite useful. So if we kind of look at a trace, we can see here that there's a graph that just kind of generate a graph of how exactly these microservices are being called one after another. So as a little bit of kind of explanation of what this graph exactly is. So this entire kind of set of bars right here, this entire graph here is known as a trace. So these traces is what I'm talking about when I'm talking about tracing, about how these different services are calling each other. So we can see here that this trace is made up of a bunch of different bars that we call spans. And these spans basically just encode a single function or a single kind of service that's being called. For example, when we clicked on the button here, we can see that that span actually called this kind of dispatch service in the front end microservice, right? And then we can see from there that that generated a bunch of smaller kind of, it made a call to the customer service that kind of made a SQL call, and then so on and so on. We can tell based on this trace here that there should be some call based in this function that calls a customer service and then does all the rest of it. And now something cool that I want you guys to kind of check out is the fact that traces aren't just encoding the latency as well as like how one service goes to another, but you can also add other information such as logging, as I talked about before, as well as tags. So logging is just basically a bunch of print statements that can help you give more information depending on kind of the event that's happening. And then tags are basically just a key value map that you add to your spans to kind of help you filter through it. So for example, what you can do with tracing that's really powerful is you can have it so that whenever you can sort based on the errors. For example, if you guys are familiar with status codes, you know that anything like 400x or like 500x are errors, and then you can kind of use those errors to kind of generate metrics based on. So if let's say theoretically that your system gets a lot of 500, so there's a lot of server-side failures, you can set up another system or metric system to kind of look if there's enough, or if there's a lot of traces that go over 500 or that kind of tell that, alert me when that happens so I can quickly fix the issue. And so that's why tracing is really used in small startups or people who want to kind of scale up, because as you scale up, you're not going to be able to kind of keep all of this information in your head at once. You won't be able to kind of know exactly when you write the code that this error specifically is going to happen. Especially as you kind of scale up with a team, it just becomes infeasible for everyone to know exactly what's going on. And for this reason, it's important to kind of keep these observability systems here. It's important so that we can kind of jump on these different kind of customer problems right away, especially when startups, the customer is king. And so for this reason, tracing is an important part of observability that I definitely suggest kind of looking into if you guys are considering scaling your kind of small side project or working at a startup. I wouldn't necessarily suggest doing it if you guys aren't necessarily scaling up, because honestly, your time is probably better invested in just creating more features and stuff like that. But if you guys are interested in kind of making a better product, adding tracing is a great way to kind of make sure that your response time and the actual time you can kind of debug stuff is a lot quicker than it normally would be. That's pretty much it for me. I have a few kind of just GitHub kind of places you guys can look at if you guys want to kind of get started with tracing. There's open tracing tutorial that kind of shows you guys how exactly do we build these spans in these services, as well as you guys can check out the Jaeger tracing that can help you guys, which is a great open source that has different client libraries in probably most modern languages. Thank you for your time, and I'll take questions now.
Great talk, Eric. So we actually do have a question right now. Is tracing also an applicable concept for monolithic apps? I know you talked about how they're used in microservices, but this person is asking whether you could use them in monolithic apps as well. Whether it's
so they're definitely like able to use in monolithic apps. Like you can definitely even use it in your CS projects if you want, because the idea is just basically like, I can even show you, I wanted to kind of show you this a bit, but I realized I timed myself before and it kind of went over a bit. So if we kind of look at the code here, it's written in Go. Basically, the idea of how tracing works is that you kind of use these client libraries that kind of initiate the tracer for you, the stuff that actually like sends it to the Jaeger stuff to handle for it to kind of create the nice graphics, right? And so this is kind of the start of the that client library. And then all you can see, if you want to create like a bar in the Jaeger UI, right? All you need to do is just, oh, sorry, wrong one. All you need to do is just start a span. You can set whatever tags, you can do whatever logs. And then if you guys aren't familiar with Go, all you need to know is that defer means that at the end of the return, at the end of the function, this will run. So what you can do is at the start of the span, you can start the span, you can do whatever you want, and then at the very end, you can finish it. So this can be used in your CS projects, for example, and then you can kind of just use this to generate all of the, like how exactly your code goes from one function to another. And then like the defer span finish just means like that's the end point, if that makes sense. So like the start is the start of the span that just tells Jaeger, oh, I'm starting at this time point, and then when you call finish, it ends the end, like ends the span, if that makes sense. And so like it's not necessarily restricted to just microservices. It's just a bit more useful in microservices because it's really confusing like how the microservice talks to each other. But you can definitely use it in monolithic applications and even in your own like CS 241 assignment or something.
Okay, awesome. Yeah, the other question is how would you add tracing into a side project? But I think you just went over that. One question I actually wanted to ask you was, so you talked about how there were metrics, logs, and tracing.
Yeah.
Those are like the three pillars of DevOps per se.
Mm-hmm.
What would you say is like the most important one to implement first?
Like when you're like considering like moving up, like scaling a project or something?
If you're considering scaling.
I definitely say like me personally, I think like logging is probably really good at the start because it's kind of a great way to debug if you haven't really scaled that much, if that makes sense. And it's really easy to implement because it's just literally just print statements. You just need to find a way to kind of send it to a collector, if that makes sense. Like it's overall a lot easier to set up than tracing and metrics are, because as well with tracing metrics, not only like you have to host it on a different kind of service or platform, but especially for tracing, a downside to it is that they tend to kind of cost a lot in terms of resources when you're sending the traces. So, and setting it up, me personally, I've had quite a bit of pain kind of setting it up. So yeah, logging is probably the best because of the ease and not necessarily because of the like usefulness to ease kind of ratio is probably the best. Yeah.
Awesome. Okay. That sounds good. Also, could you go back to that last slide so I can put that link in the chat? So you reach Kuro Open Tracing. We'll be putting that link in the chat real soon.
Okay, cool.
Other than that, I think great presentation, Eric.
Thanks.
I think I learned a lot from that. Okay, so our next presenter is Adi, and he will be our final speaker for the night, actually. He's a CS 2021 alumni, and he'll be giving intro to metaprogramming in TypeScript. Welcome, Adi.
Sorry. Hey everyone, I'm Adi, and today I'm going to be talking about metaprogramming in TypeScript. So for those of you who don't know, TypeScript is a programming language that came out in 2013, and instead of compiling to bytecode, it compiles to JavaScript. And it's a superset of JavaScript, and it basically just adds static typing to it. So JavaScript plus static types is TypeScript. Okay, so before I go more into details about TypeScript, I can introduce myself. So as I mentioned, I'm Adi. I graduated from the CS program from Waterloo during the winter term, and I've been using TypeScript since my second co-op in January 2018. I've also used TypeScript in a lot of my interviews, so I'm pretty familiar with it. Initially, I was kind of hesitant to use TypeScript when I started learning it, but as I got more and more familiar, I just did not want to go back to JavaScript. Okay, so before I talk more about metaprogramming, let's kind of go over the basic stuff and what types are in TypeScript. Okay, so types can be thought of as sets, right? So the set of Boolean the Boolean set has two values in it, right? So true and false. And then the set of numbers has all the integers and all the floats, right? And then the set of strings is an infinite set that contains all valid strings in JavaScript. And then even custom types like this can be represented in somewhat of a set notation. So we can say that for all first names in string, for all last names in string, the object with first names is F name and last name is L name is a person. So we have another infinite set. All right. So let's say we want to represent a box of items, right? So how can we, and then this item could be of any type. So how do we represent this? We can create an interface, which is a box, and each box can have an ID. And then it can also have some data, and then we're going to give this type unknown. It's unknown because when we're creating this interface, we don't really know what the data is going to be. And yeah, so while we create a box, we know that this is a string, the data is a string, but then later on, when we try to access this data from the box, the compiler no longer knows that it is a string. But as a developer, we know that it's clearly a string and it's not going to change, right? So that's a problem. So that's where generics come in. So you can think of, so basically, now we're creating a box which takes in an argument. So you can think of this as like a function argument, but for types. And so this is a type, and we're just going to say that we're going to specialize this box with some type of thing, and then that type is actually the data that you're holding. Okay, so we can say that a string box is a box of string, right? And so this is called specialization, and it's very similar to calling a function with some parameters. So we can put a string in this box, and then we can put a number in this box, and later on, when we try to access this, the compiler will know that this is a string, and then this is a number. Okay. So what else? So what if we only wanted boxes of strings and numbers? Then we can use this extends keyword along with a type union. So just like you can have a union of sets, you can also have a union of types. So in this case, this essentially means that this is a new type, and this type is a union of string and numbers, right? And so we can create boxes of strings, we can create boxes of numbers, but we can't create boxes of booleans because the boolean values are not a part of this type. Okay. Now let's say that our boxes have more boxes inside them. We want to be able to look at the type of the item in the innermost box very easily. So essentially, can we open a box or a box of a box or a box of a box of a box and so on and so forth, and easily take a look at the type inside it. Yeah, so we can do that by using recursive types and type inference. So that's what the infer keyword is used for. So we create a new type, and it takes a type argument. So that's t, right? So we're gonna check that if t is a box, and then what this is essentially doing is something like this in math. So when you say that unbox of a box of a box of a string equals an unbox of a box of data, then data is clearly equal to this, because the left and right hand side have to match, right? So that's what the infer keyword is doing for us. So it's asking the compiler, when we're specializing this type, what is the innermost type? Well, not the innermost, but what is the thing inside the box? And then give whatever that is, give it the variable data. Okay. So if data is a box, so which means if this is a box, then we're going to unbox the data. So that's a recursive type, right? Because we're kind of going in. And then if the data is not a box, right? So then we're just going to return the data back to it. And then if t is not a box, then we're going to use the never type. So the never type is basically means that a value of that type can never exist in JavaScript. Okay, so these are the examples for what I just described. So it's a string box, and this is a string box. And then this is going to give us a string, and this is also going to give us a string. Okay. So, but what is metaprogramming? So, metaprogramming, based on Wikipedia, is a programming technique in which computer programs have the ability to treat other programs as their data. So essentially, what we're basically going to do is do the computations that would have happened on runtime. We're going to move them to compile time. So that's like one of the benefits of metaprogramming, and then this is kind of what we're going to focus on, and not really the broad metaprogramming part. Okay. So, oh, it was stuck. Sorry. So for the rest of the talk, I'm going to be taking examples from the metaprogramming package, or metatyping package, sorry. And a lot of the code in the slides has been more or less directly copied from that package. And it's kind of fun. So first of all, we're going to try to increment and decrement numbers on compile time. So remember, none of this is going to produce any code. All of this happens on build time or compile time. So since TypeScript does not really have arithmetic, the type system of TypeScript does not have any arithmetic, right? So I can't just say type 2 equals 1 plus 1. So we're kind of cheating here a little bit, and we're just producing a table. So an increment table and a decrement table. So essentially 0 maps to 1, 1 maps to 2, and then so on and so forth until 9 maps to 10. And the same thing for the decrement table. So the way we implement our increment type is just we check that the type argument that it got is a key inside the increment table. And then we're just going to return whatever that value maps to in the increment table. And the same thing for decrementing it. And so this is kind of how we get the results or the types. This is a little bit dry and kind of boring, but there's a pretty big reveal at the end, which kind of highlights how powerful the type system actually is. Okay, so we need a bunch more kind of utilities so we can implement something big, right? So we're going to implement less than or equal to for numbers. So if A is smaller than or equal to B, it's going to return true, and then if it's not, then it's going to return false. So remember how we only have 10 numbers. And then when we increment a number, if it's not there, then it's just going to output never. So if we try to increment 10, it's not going to say 11, it's going to say never, because in our type system over here, we can only represent 10 numbers. So right, so what we're basically doing is we're incrementing both the numbers by 1, and we're depending on which number reaches never first, and based on whatever it does, we're going to say true or false. So for example, if we want to check if 8 is less than 9, then that's the same as checking if 9 is less than 10, which is the same as checking if 10 is less than never. And that's the same as checking if never is less than never, which is true by this logic. And so the other way around, if you want to check that 9 is less than 8, so that's the same as checking if 10 is less than 9, which is the same as checking never is less than 10, which is false. So if A and B are both never, then A is less than B. If A is never and B is not never, then A is not less than B. Otherwise, we just increment A and increment B, and then just use recursion again. All right. Okay. And so we also have some utilities for getting the head and the tail of a list or an array, right? So basically, we have a type argument t, and then if t matches this syntax, so basically if it has a thing in the beginning and then anything after that, then we output t0. If it does not match the syntax, which means that it's an empty array, where we output the never type. And the same thing for tail, but we use the infer keyword over here. So it starts with something, and then it has a bunch of other things after that. Then we output the bunch of other things. And if it only has one thing, then we output never. Oh no, actually, we don't output never. If it's an empty array, then we output never. But if it doesn't have anything else, then we output an empty array. Okay. Okay, so time for the big reveal. So we're gonna implement insertion sort. So this is a type that inserts a number into another type. So the first type is a number, and then this type is an array of numbers. And so we're going to check if the return type is an empty array. So if the return type is an empty array, then I mean, all you need to do is output an array with one element in it, and that's sorted, right? If n is less than the first element inside this thing, then all we need to do is insert it before the array. So we output n and then the rest of r. If it's not, then we need to recursively insert it on the rest of the elements of r. So we output the head of r, and then we insert it inside the tail of r. So I also need to use some casting over here because it wasn't really working in modern TypeScript versions, but it was working in earlier versions. So I just used a little bit of casting over here. And then, so how do we implement insertion sort? So insertion sort takes in a type, which is our array that we want to sort. And then this is just the accumulator. So it has a default argument of the empty array, right? So if T is empty, then our sorted array is also empty. So we're good. And the way we sort it is we insert we take the first element from this array and then insert it in this one using our insert utility. So we, if you know insertion sort, we build up a sorted array. So let's check out what it looks like in the playground. Gonna zoom in a little bit and wait for it to load. Okay, cool. So that's our increment table. We can increment things, add tail, is never, which is a small utility, right? And so we have this unsorted array as a type, right? So 6, 9, 7, whatever. And then if we hover over this, we're going to get a sorted array type back. And so this is a test for the insert utility. So if we want to insert 3 inside an array, which is 1, 2, 4, and 5, then it should be 1, 2, 3, 4, and 5. And yeah, so that's how you implement insertion sort, only using TypeScript types, which don't really output any code. So that package that I mentioned earlier, the meta typing package, that has a bunch of other utilities as well. And it also solves a bunch of other puzzles. So it implements quicksort, merge sort, insertion sort. It solves n-queens problems. It solves maze, like a maze solving problem. There's something about binary trees as well, and other things too. So it's kind of fun, and you won't use this stuff every day, and definitely don't use it for interviews. But yeah. And I'm opening the floor for questions now.
All right, yeah, that's pretty sick. Now, I was actually thinking that I could probably use that for my LeetCode interviews, so I could do my solution 01 during build time. But I guess I guess I can't. But we actually do have one question right now, and it's about TypeScript specifically. Is there a TypeScript feature that particularly broke your brain when you learned about it?
Broke my brain. Not really. I don't think I don't think it ever, like, it was pretty straightforward to learn. Like initially I was having some problems with like grasping types, because I'd already done a project in JavaScript earlier, but just using JavaScript with types was kind of mind-boggling. And also I was in second year at that time, so it was like kind of hard to understand another new language. But now that I have had more experience working with other languages as well, and like honestly, if you're familiar with C++, somewhat familiar with C++, you'll be just fine. So you're not going to have a lot of problems.
Okay, sick. Yeah, actually, on that note, you said it reminded you of C++, and it definitely did remind me of like generics in C++. And so I want to ask you, is this used a lot in practice, like in like how you would use generics in C++, or is the recursive aspect of it used more, if it is used in practice?
So in practice in C++ or in TypeScript?
In TypeScript. Like,
right. So recursive types are actually used in a lot of places. So for example, that unbox type that I just described, I think that's very similar to how Rust does things as well. So Rust, in Rust, you can create a box, and I could be wrong here, but it's essentially the same as a pointer. And then if you want to get the type that a pointer to a pointer to a pointer and so on and so forth, what the actual type, the innermost type is, you'd actually use something like this in Rust as well. So, and in TypeScript as well, like if you're implementing a function that kind of takes in an argument, which is kind of, I don't know, it could be a string or a number, or it could be an array of strings or numbers, or it could be an array of strings and numbers, and so on and so forth, right? So you kind of need a way to get that innermost type. And so in those scenarios, you'll probably be using recursive types.
Okay, yeah, that makes sense. And we have one final question. So you showed that this could actually solve a lot of like big algorithms that we see in like our algorithms courses. But the question is the type system Turing complete? They know that the C++ templates are, and it looks very similar. Yeah.
So I think it is Turing complete. I looked at an issue on the TypeScript repository, and that implements a bunch of other stuff and proves that it's Turing complete. I don't have a link to it right now, but I think it is Turing complete. Also, there are other links on this package as well, and someone actually implemented a 4-bit virtual machine. So that's kind of cool. And so I think that it is Turing complete, although this is, I don't know if this is a metric of if it is Turing complete or not, but probably is, yeah.
Okay, awesome. Yeah, so that's all for Q&A we have now, and let's move on. All right, so that wraps up this term's Alt Tab Talks. Thank you everyone for tuning in. If you want to help us improve the event, please fill in the feedback form at bit.ly/alttabfeedback. If you're interested in learning more about any of the topics from today's talk, be sure to join CSC's Discord at discord.gg/UWCSClub. Thank you to all the speakers for your interesting talks, and thanks again for everyone for attending. Have a great night. See ya.